Thank you so much for being here. It's a great pleasure to talk about something I love, and I'm sure everyone here enjoys doing, which is programming. I program in about 15 different languages. What I mean by that is I'm not good in any one of them, but I love programming. And I often say that I started programming because of the love I had for math and physics and science in general. About 35 years later, I'm still a programmer because of the art in programming that I see. So I want to talk a little bit about what do I want to see in programming languages as we move forward. Over the years, as I've programmed in multiple languages, I've kind of enjoyed some languages more than others. And I want to talk a little bit about where things are today and where things are heading, and we'll talk about a few examples along the way as well. Well, first of all, of course, this is something we have heard people say over and over and over to us, right? They say that things change really fast in our field. And sure, that's true to some extent. There are a few things that change really fast. But let's talk about how we actually write code in the new century. I'm sure a lot of us still see that kind of code, isn't it? And over and over and over, we write verbose code. And how does it feel to be writing such code? And when you look at the field itself, I started programming back in the 80s. And over the years, I've learned a few different languages along the way. And in my journey, I would say there are a few things that have been really challenging. Learning a language is not really that hard, but learning a paradigm takes a lot more effort. And I'm going to say maybe I've gone through about 5, if not 6 paradigm shifts. The first paradigm shift I went through was beginning to learn programming. I could never forget those early beginner days when I was struggling to learn programming without even having a computer, which is really hard. And I did algorithm on papers. I had a really good uncle who inspired me to learn about programming. And paper was my compiler. He was my compiler. He would read through my algorithms and suggest things to change. And then, of course, the first language I learned was somewhat between C and VB. I spent a few years programming in VB. So paradigm shift, first of all, was learning to program. The next paradigm shift I came across was object-oriented programming. I know it's kind of hard to imagine for a lot of people, younger people today, but when I started programming, there was no object-oriented programming in mainstream. And then seeing that evolve over time and learning about object-oriented programming. The third bigger paradigm shift for me was really learning about distributed object computing. There are days I would wake up, honestly, with a cloud over my head, not understanding what in the world does it mean to use an object factory to get this object that exists in a remote system. And these days, of course, I really fear that one day my children will get to know that their dad actually used COM and Corba. I don't know what they would think of me if they find that out. But that was a big paradigm shift for me to really understand how to do remote computing. But then, of course, came along a bigger challenge eventually. I was trying to really learn about JavaScript. Now, of course, JavaScript itself I'm not saying it necessarily is hard because it's evil. It is. But the point really is that it really took me a long time to wrap my head around asynchronous programming. What does it mean to program asynchronously? That was a leap for me to really understand, especially because I was not satisfied writing just another callback and going home. I wanted to understand how these things behave, how these things work. And so that was a really big paradigm shift. Then probably a bigger paradigm shift for me was to learn about functional programming. I came about 20 years into it with programming an imperative style, an object-oriented style. And what really made it hard for me was the people who knew functional programming. And they often said, oh, it's really easy. Well, it was not. It was really hard to think a different way than what I'm used to thinking in imperative style. So that took a lot of journey to understand how to program in functional style. And then, of course, eventually I came across reactive programming. And I have to say, I got really angry when I looked at reactive programming because a lot of literature was hand-waving and telling how awesome this is and how you can do architecture with reactive programming. And I'm like the guy who says, show me the damn code. I have to see how things actually work programmatically. And my realization over time really was that reactive programming is really functional programming plus, because you're really building on a foundation of functional programming and raising the level of abstraction in doing so. So the paradigm shifts are really the most challenging for me than programming languages. So when people ask me, what language should I learn, I often tell them, don't pick a language to learn, pick a different paradigm to learn. Because when you learn a different paradigm, you learn a different way of thinking, which is really what you want to do. So if you know Java, saying that you're going to learn C# doesn't count. Go pick up something that will hurt you, that will make you cry, that will make you beg for mercy. Then you're learning something interesting. It changes the way you think, and it changes the way you program and design as well. That becomes very effective. So certainly some things are really hard to change over time, and I think we can agree to that. For example, we talk about Turing completeness. Well, sure, why would you want to use a language that's not Turing complete? So that, to me, is a pretty low bar in a lot of ways, because Turing completeness often doesn't talk about efficiency of programming or the speed at which the code can run or the elegance of the code. None of it really addresses in that regard. So sure, we want to think about Turing complete, but we have to go beyond that in a lot of ways when looking at languages. And sure, there are going to be still bottlenecks to worry about in terms of moving objects around or data around memory. That often becomes a challenge, especially when we do distributed computing and when we are trying to really do all these architectures we are trying to implement these days. That becomes a challenge as well. But let's think about this from the past to really think about where things have been. So if you think about object-oriented programming, if you ask people, when did object-oriented programming really become popular? I would say that's about 1990 timeframe is when it really became popular. I remember spending my young days as a programmer where I would constantly see this fight between people. One group saying object-oriented programming really is amazing, and the other people saying it really sucks. And there would be debates about how systems would be really poorly designed, it'll be slow. And then all that conversation just faded away into the past, and people started not only using objects, but overusing objects over the years. And that happened, about 1990 and a few years after that. But shockingly enough, when was object-oriented programming really introduced? Well, as it turns out, it was introduced in 1967 by Dahl and Nygaard. Now, let that sink in for a minute. 1967 to 1990. That is a clear 23 years if you think about it. Now, if it took 23 years to become mainstream, would we call that really fast? And when somebody tells me things move really fast, I often ask them, really, what are you smoking? Because things don't change as fast as we think it actually changes. It took 23 years. Now you say, but what is 23? Well, think about what 23 is. A child that's born goes through school, goes through college, finds his or her first job, and takes up a work. That's 23 years. What that is called is a generation. And this really clicked in my mind because I didn't realize this until an event happened. I was giving a keynote in a conference. I finished my keynote, got down off the stage, sat down. There was a young lady sitting next to me, and she said, thanks for the talk. I said, you're welcome. I'm glad you're here. And she said she's been through a master's degree, and she's been working for 2 years. When somebody says they have done a master's degree and they work for 2 years, it doesn't take a rocket scientist to know how old they are. Do a little math, you can put the numbers together. I said, that's nice. I'm really glad that you are working in the industry. And then she said, can I ask you a personal question? I said, thank you for coming, but I don't do personal questions, but thanks for asking. No, I really need to ask you this question. Please, one question. I said, no, lady, we don't do personal questions, but anything technical, bring it on. I'll be happy to talk to you. And she said, no, I really liked your talk. Just allow me one personal question. I said, fine, what's your question? I can try to answer it. And then she said, what year did you graduate from college? I said, no. We're not doing that. She said, please tell me what year you graduated. And I told her the year I graduated. Her face just blossomed, and she said, oh my gosh, that's the year I was born. And I was like, I don't know how to respond. I looked at her for a few minutes, and I said, can you do me a favor? She said, what can I do for you? Can you reach over the cane for me? I need some help walking. And I just realized that somebody who is as old as my children, is a colleague in the industry, so to say, is working in the field together, and suddenly I felt like a burden has been lifted off my shoulder because it's no longer my own responsibility, so to say. There's a younger generation that's come up. And why do things take 23 years to change? Because it's a new group of people who are looking at us and saying, why are you guys doing this? Isn't there a better way to do? And so every generation comes and moves the field ahead. And so changes happen in increments. But the increments happen by generational change. And I'm not suggesting that everybody doesn't want to change, but a lot of us have difficulty changing because once we establish what we do, our desire is to maintain the status quo until a group of people who come along, the next generation typically, who don't have that burden, who don't have that baggage, so to say, but want to move forward and is interested in moving ahead. This really is even further intriguing when you think about where things are today and what are we excited about. Well, talk about functional programming. A lot of us are interested in functional programming today. We talk about it in different languages. Most mainstream languages today support functional programming one way or the other. I would say most languages are really hybrid languages today, which is intriguing. But once again, if you go back and look at history, when was lambda calculus, the foundation for functional programming, when was that created? Well, everyone in this room knows of Alan Turing. Well, this was Alan Turing's professor, Alonzo Church, who created lambda calculus in 1929. Now, just think about that for a minute. A good 90 years later, we are just super excited about this stuff. Things are changing really fast, isn't it? So things, again, take a long time for things to take root. And things have to prove themselves for us to be able to adapt to it. So that takes almost a generational change, and we take these changes in bite size, but it takes a new generation. But of course, we are poised for our next generation of change again, and this started about 2003 to 2006 timeframe. Again, if you think about it, a good 20 years ago, almost. And this started happening when the world around us changed because the hardware decided to change, and also the business world decided to change. This is the fun part of what we do. Around us, we have two things. Whom do we run things for, and where do we run them on? And both of these kind of force change upon us, even if we don't want to really pick up and start changing. And of course, when you think about it, there's a lot of stuff going on around us that really is intriguing and forcing changes to what we do, and we are really trying to respond to these kinds of different ideas and changes as well. But yet, when you think about it, how do we really build web applications? If you think about how we build applications, unfortunately today, it is still a stateless world. You send a request to the server, which then, of course, sends a response back to you, whether it's HTML or XML or JSON, and you are getting the response back from it. And when you think about it this way, how does it feel to build this application? I feel a little animated oftentimes, and I often relate this to, remember this interesting movie, Finding Nemo? In the Finding Nemo movie, there is this character called Dory. And every few minutes, Dory says, "Hi, I'm Dory." That's how I feel creating web applications. Because you don't really have a state you got to reestablish, and this is really a burden for us to continue. What if things can be different? Well, thankfully, this change is already happening with a lot of languages introducing and libraries introducing this idea of continuations. And I'm really keen about continuations because this idea truly intrigues me. There are a few libraries and frameworks that do this already, but I think in the next few years, this is going to take a lot more prominence in what we do. Continuations is a way for us to save the state of execution and then resume from where we leave. So imagine having a conversation with an application where it responds back to you, but when you get back to it, it can pick up from where it left off and move on. So the state can be in the conversation rather than stored elsewhere to be restored back. So this is an idea that I'm really looking forward to. But when it comes to languages, I'm a language geek. I'm really keenly interested in programming languages. And I have this luxury, and I say this luxury because I have this luxury to do things what others often may not be able to do, which is I can write some code and literally decide to take next several hours just staring at the code and improving it, because I have a very different perspective of what my priorities are compared to a lot of other people. I've got the luxury of doing research, I've the luxury of delivering for my clients, but I get to choose when I want to do it. So oftentimes I would sit with the code and, pointlessly, sometimes people say, but I really want to keep working on the code until it can be better. At least to my eyes, it can be better. So what do I want to see in programming languages? And I would say the first thing I want languages to do is that simple things must be simpler and hard things must be manageable. If simple things are really hard to do and hard things are incredibly difficult to do, that really impacts our productivity, and our expressiveness becomes really hard to maintain applications as well. So in that regard, I would say languages must promote a higher level of abstraction. And a higher level of abstraction reduces complexity for us to program and becomes a lot easier for us to work with. And I care about composability and declarative style of programming as well. Well, first of all, I like to have languages that are really expressive. And what I mean by languages that are expressive is I want the language to be really intuitive to use. I want the language to think like me rather than me thinking like what the language wants me to think about. For example, just to think about one example here, I was working with Kotlin one day, and just as an example, let's say I have fruits over here is equal to list of, let's say I have apples, and I have, let's say, oranges over here as well. So when I have these little objects, and I was working on some application where I had a collection of these different objects to work with, and I'm going to just display the fruits over here and see what the output is going to be. And obviously, in this case, you want to see apples and oranges. But I was working with this application where I had a collection of data, and all I really wanted to do was to add a data to this particular collection of objects. And as I was coding, I suddenly thought about it, and I said, wouldn't it be really nice if I can simply say, bananas, for example, and just add to it? And the minute I thought about it, I said, but why not? Why shouldn't I be able to do it? And I didn't even care to look at a documentation or anything. I just ran the code, and to my surprise, of course, it was able to really accomplish the job. And I can't tell you how much it makes you happy as a programmer when you think something and then the code actually works. You don't have to go look for a documentation to do it. So this is an example of how I want things to be expressive. But expressiveness goes really far beyond this as well, quite a bit in terms of what we can do. So as an example, let's say we have a person, Sam, equal to, we'll say name is going to be Sam, let's say, and age is going to be 2 for a minute. And sure, this is JavaScript, but that's okay. I think we can learn from anything in this world. And so in this case, I want to just show you something I really appreciate, and I want to see this more in languages. So let's say for a minute, I want to say over here, I want to create older Sam, let's say, call it older Sam, is equal to, I'm going to say name is going to be sam.name, and I could say age is going to be, let's say, sam.age plus a 1. Now, obviously, when we finish this, we can print out Sam, we can print out the older Sam as well, but the problem with this code is it simply is not that expressive. But more important, there are a few problems. And this is one of the things I really like to do, is to not just write code and walk away, but write code and stare at it and say, what does this mean? What are the consequences of writing this code? And you might realize it, or you might not realize it, that there are 2 problems with this code. The first problem is it violates the dry principle. You're duplicating the effort to write this code. And yes, it's minor, but that's how problems really start. A little at a time, it deteriorates and becomes a problem over time. The second problem with this code is a little bit bigger. It violates the open-closed principle. The open-closed principle says you should be able to extend a software without actually having to modify it. Now, these little things can result in code that takes effort over time to keep changing over and over and over, results in bug, and we often say, oh, darn it, I didn't realize I got to change that piece of code, now I did it. Now, what if we can write this code in a way we don't have to violate these principles? We can keep it dry, we can also make it extensible. Well, this is where I think I really look at languages. I don't look at languages as syntax. Language syntax is the least interesting for me. When I look at languages, I look at design principles, I look at design ideas, design concepts that are in the languages. So when I go back to this code, I want to simply say, here is Sam, and grab everything from Sam, and here is age, I want to update the age. What's the benefit of this? The benefit, of course, is that if I were to modify Sam, and maybe Sam has a social network ID that exists here, I don't have to make a change to the code right here because we are grabbing everything from the object. It is extensible. So these kinds of features are not simply syntax sugar. They actually have a deeper impact in what we do. They affect our ability to design software, to make it extensible, to make it less verbose. So it's expressive code, but expressive code often leads to better design than a code that is not expressive as well. So this has a greater implication. This really goes back to, I'm a person who gets really excited quite easily oftentimes. And one day I was programming with Kotlin, I was programming with JavaScript, and suddenly I made a kind of a silly tweet, and my tweet was really this. Today's tweet is sponsored by destructuring, I said. I have to admit, destructuring is turning up to be one of my most favorite features in the language. And a few minutes later, Brian Getz, who is the chief architect behind the Java language, said, I can neither confirm nor deny that Java will have some cool destruction feature in the future. And I replied to him saying, I think I know the answer already, and I cannot start really using destructuring in Java. And the point really is, this is one of the amazing concepts in programming that is taking root, and languages are beginning to support this notion of destructuring that can make our lives a lot easier. For example, if you really think about it, the point that Brian continues to make here is destructuring using a use site versus a declarative site, but even more towards moving towards functions that can start destructuring so that it can communicate its structural information to the caller. Imagine that idea for a minute. The structural information to the caller can be really, really effective. For example, let's say in this particular example, I have a height, let's say, of some value. I have a weight, let's say, of some other value here, whatever that value could be. Now, if you take this particular example here, how would I go about using this particular information? Well, the beauty of this is we can take this and say, let's say process information is a function. I'm going to say process. I can send Sam as an object, and within this, of course, I can use Sam. So we could call the process function right here, and we can send Sam here as an object. This is a traditional way we are all very used to, and we can do this. But what if more languages begin to support this particular feature where you simply communicate that you want to receive, let's say, the age value because that's all you really care about? So in this particular case, you can print the age, and you can extract that information, and you are conveying that you don't really care about any of the other properties. So this can be really an effective way to apply destructuring while you are actually processing the object in a function parameter. One of the things I often look for when I learn programming languages is some of these kinds of capabilities. I learned to program in Erlang, not because I want to use Erlang in production. I've never put a Erlang code in production, but I learned just to learn Erlang because it really intrigued me about the nature of the language being a dynamic type language, but also how pattern matching is really effective in Erlang. So that really led me to think about these styles of programming, and I tend to explore some of these things. So when it comes to languages, I really want languages to be expressive, and an expressive language, like I said, influences deeply your ability to design extensible software as well that has a good ramification to what we do. Excuse me. Similarly, I would say that I really look for composability with programming languages as well is another feature I really care about. Let's talk about composability just for a minute, if you will. For example, let's say I have a list of names over here. We'll call it as some names over here. This is a beautiful Java code, as you can see right here. And I'm going to say, here's a list of names, but I can then take that off and say, for instance, we could say a filter, and I could say, given a name, I could say name.length. Maybe in this particular case, I want length of, let's say, 4, and I want to map this to maybe uppercase lowercase, I'll say to uppercase right here. And then once I do, I want to simply, for each of them, I want to really print out, and we could say print line, and we can print it out right here. So essentially, in this particular case, you are dealing with, again, a code that really composes through, and this can be really effective. Now, as much as I really love Python, this is one of the things I complain about in Python. To me, Python code is not as composable because you kind of draw it inside out with function calls and parentheses around it. But if you really personally ask me, I would really prefer F-sharp-like of composability, where you can take the names, but you can simply do a beautiful, if you will, where it is very natural for me to think about, I could apply a filter method right there, and then I could do another method. For example, in this particular case, I could do a map method here as well, and so on. So to me, that composability really makes me think along a flow of data. And when you think of a flow of data, this naturally falls in place with a lot of things we have been doing for decades, if you will. For example, if any one of us who has programmed in Unix-like system, what do you normally do? You take a source file, and you normally send it through something like a grep, for example. And then you grep for certain words, if you will, and then you could pass it through an awk or a set command, and maybe other commands like wc and so on. And if you really think about it, what you're noticing is the filter, map, and reduce are really the patterns we've been using for a long time, maybe without even realizing it. So the composability is a very important characteristic. Unix has shown us how we could do composability, and more programming languages are showing us how composability can be really helpful. That is something I really care about as well. But then, of course, one of the other things we are really keen about these days in what we do is efficiency. And this is something for us to keep in mind quite a bit when we look at code, because efficiency is extremely important. Let's go back and look at this code for a minute. Maybe what I really want here is for each, and let's say find first, and I want to get the very first value out of this. And once I get the first value out of this, I'm going to store this into a variable, result is equal to, and I want to really, let's say, print out the result over here. So when I run the code in this case, the first one we get here, I'll even say .or else, and I'll simply take an empty string, and the result here is Dory. Let's change this just a little bit for our purpose right here to see this. I'm going to say 5 over here and run the code. The result is obviously Bruce. But when you look at this code, what is the benefit of writing a code like this in functional style? I'll share with you a story about it. I was in Seattle to work with the team, and a developer, they were developing application with C#, and a developer said, hey, we've been transitioning more into functional style code. I want to show you some code I've written. Can you take a look at it and comment on it? And usually I'm a little scared when people ask me this, because I don't know anything about their code or their application. And the worst thing I can tell them is, gee, sorry, your code sucks. That's not going to really make good friends when you feel that way. But I often like to say the truth. When it sucks, I say it sucks. So I was a little apprehensive. I said, sure, I'll be happy to look at it. And he shows me a C# code. And to my surprise, even I could understand the code. I started reading the code. It said, we got shipments coming in, and when you have the shipments, filter on these shipments, and then after you filter these shipments, look for these kinds of more things in shipments, transform this using the select and where. And I'm like, oh my gosh, I'm actually able to understand this code because the code is reading like the problem statement. And I said, kudos, this is really nice. I'm able to understand this really well, which is the point of functional programming is it removes the accidental complexity from your code. However, there is one concern we need to be really thinking about, and that is, what does this code actually do? If this code is going to take every single value in the collection and check if it is of length 5, that's going to be 1, 2, 3, 4, 5, 6, 7 computations. After 7 computations, you map everything to uppercase that's of length 5. In this particular example, that's 2 words of length 5, I think. And then you find the first one and you discard everything else. How terrible that would be for you to do all that work only to throw out most of the work you did. Now, this is the theory that I have. when you look at this code, I think we can all use this word, it is cute. And sure, it is cute, but I have this theory that both in life and programming, cuteness does not last very long. This is the problem. You know, my wife and I love children. Small kids, we dearly love them. But when a friend of us calls us and says, we got a newborn, we rush to the hospital. We want to look at the kid. But I'm the pessimist in the family, I think, comparatively speaking. My wife will look at the kid and say, how cute. And I would lean over and say, don't listen to her. This doesn't last too long. And cuteness for humans lasts for 2 years of their age. I was in Portugal, and I was traveling with a gentleman. Both of us are programmers. We had 3 hours to spend in the car. What do? We talk about programming. We talk about garbage collection. We talk about memory leaks. We talk about concurrency. And eventually, we have to talk about other things. So I'm just sitting there in the car with him. And then he eventually says, hey, do you have kids? I said, yeah, I have kids, but they're all grown up. And then I said, what about you? And he said, I have a 2-year-old. I said, oh my gosh, that's wonderful. Having a 2-year-old, I can only, vaguely remember the time when we had a 2-year-old. And then I said, how's it going? And he said, it's mostly okay. I said, mostly okay, what's going on? And he said, well, 3 weeks ago, at 3 a.m., she woke up and began to sing. And I said, that's cute. And she said, well, it was the first day. And now, every day at 3 a.m., she wakes up and sings, and we tell her at 3 a.m., shut up. So the cuteness goes away eventually, isn't it? Well, that's the problem with a code like this is, it's very cute, but the P word comes into question. What about performance? So efficiency is extremely important. So if I go back to this code for a minute, and if I were to say, for example, let's remove that for a second and say that I have a name, I want to call it transform, and pass the name to it. So back here, I'm going to say, let's say a public, a static in this particular case, will say a transform, takes a name here, and all it's going to do is to simply return name.to uppercase and return that particular object. So I just rewrote the code doing exactly the same thing. But I want to say, in this case, transform called for, and I'm going to say the name and execute the code. And what you notice is the transform was called for Bruce. Now, similarly, though, if I were to do the check over here, just to illustrate the point here, if I were to say check and pass the name to it, where I'm interested in a size of 5 after all, so let's say Boolean, we'll call it as check. And in this case, I'm going to simply say return name.length, let's say, is equal to 5, as we did a few minutes ago. But I'm going to ask the question in here, check called for, and I'm going to say what was it called for, and display the name. You would notice in this particular case, it was called for Dory and Gil, but notice it did not bother to touch anything after Bruce, and it doesn't matter how long this collection is. Once it finds the result, it's going to bail out. So this is one of the important characteristics of any language is not just cuteness. So cuteness plus efficiency is highly critical. So we cannot simply have cuteness and walk away with it. So when I start learning programming languages, what I often look for is not only is it expressive, but is it really efficient? So what does efficiency mean in this particular case? Let's relate this to something more practical that we can think of. On January the 2nd, the boss calls you and says, there's an important project, it's due on April the 1st, and you're going to work on it. So what do you do right after this meeting on January the 2nd? You go back to your desk and immediately start working on it, right? No, thank you. No, right? Everybody had that in mind, but thanks for saying it. No. What do? You don't start on it on January 2nd. You say, I'll get to it later. And when do you get to it? Well, sure, the boss can wait on it, but there's something you know the boss doesn't know, that you already plan to quit on March 1st. Why would you start on this project? What is that called? Efficiency, isn't it? Because you would rather do other useful things than start on the project that you would never actually be there to finish, and that's called efficiency. that is one of the key things in functional programming is that when you think about languages, I want to think about some of these things. And I want to say that functional programming relies on a lazy evaluation for efficiency. But of course, this is just the beginning of the story. A lot of times when we talk about programming languages, about functional programming, people often hammer on us and say, you will make things immutable. Well, unfortunately, though, telling programmers that you have to make things immutable is like telling children that they have to eat vegetables. No wonder nobody likes these ideas. So the question is, why is this important? And the reason really is that lazy evaluation, if you think about it, lazy evaluation relies on, you could say, purity of functions, which really translates, in effect, to really immutability is part of it, for actually correctness. So you cannot make your code correct if you start mutating things in functional programming, because functional programming relies on lazy evaluation for efficiency, and lazy evaluation relies on purity of functions for correctness. So these things really come back to language design. When you look at languages like Haskell, for example, or Erlang, purity is enforced in the language. The language is extremely opinionated in the sense that it'll tell you that you cannot mutate things, and it would watch over what you do. If you're programming in a language like Haskell, you don't just write code and walk away. When you come back home and you're at the dinner, sitting and eating, and you realize that Haskell is sitting in one of the chair and watching you, and it's telling you, I'm seeing what you're doing. No, that's not what you want to do. It's extremely opinionated. It will not allow you to do things that lead to incorrectness in that sense. But languages like C# and Java and Python and Ruby and Groovy and Kotlin and TypeScript and keep going, a lot of these languages, unfortunately, are hybrid object-oriented functional style programming language. So these languages cannot enforce to you what would otherwise be possible. So it's on us to really take care of these things to provide efficiency and correctness as well. And finally, I will talk about one other feature that I really care about, is that asynchronous programming becomes extremely important. And in today's world, you want to be able to say that you can program asynchronously, and I do have a bit of a complaint to make, if you will, because again, this is something I care about in programming languages. Let's talk about Kotlin for a few minutes before we talk about other things. In Kotlin was written by programmers who not only care about programming, but they care about humanity. So when you program in Kotlin, you write the function by saying fun, first of all, and you say fun, and you define the function name task1, and you can specify what it receives as an argument, and so on. Well, they call it fun because they really want you to have fun when you program. That's extremely important. So you're defining a function, but in the case of Kotlin, you can say that a particular function can be interrupted while it's executing, and you will let go of the thread, and you can be non-blocking in your code of execution. So how do you say a function is non-blocking? Now, as much as I love Kotlin, I do have a complaint to make. I really wish they had consulted with me before they named it. Because if they asked me, I would have said, call this non-blocking fun. Wouldn't that be really cool? A non-blocking fun. Somebody said non-stopping fun. But very sad, they called it suspend fun. How terrible that really is. But anyway, that's my official complaint about what they did. But notice what they are doing here in this particular case. They are telling you that this function is a synchronous function, but this one is a asynchronous function. And to me, those things are extremely important. Now, what does that do for us? It gives you that little thing to notice that this is really asynchronous, that is almost seamless. If you look at C# versus Java, for example, when I write a functional pipeline in Java, I use the word stream, but in C# I don't. Well, in C# you got to know that it's a lazy evaluation. In Java, it's a little bit more explicit, that almost seamlessness points to you. But the same token in Java, for example, they have virtual threads now, but there's no way for me to tell that it's asynchronous. I'm not really happy about it because how do you know if a function is asynchronous? Well, read the documentation. I'm not suggesting you don't want to read the documentation, but I don't want to be forced to read the documentation and know the obvious things because that's cognitive load for me. So I want the code to be almost seamless, but not entirely seamless at the same time. I don't want it to be verbose, but I don't want to be totally seamless as well at the same time. So what can we expect the future to have? Well, the future is changing. We got a lot of interesting languages, but the question is, how can we prepare towards that? And the answer to that question really is that learning different languages can be very beneficial. In what way? I'll relate this study really quickly. In Chicago, they were doing research with a small group of children, very small children. They had one group of children who only got exposed to one language. Doesn't matter what that language is. They could be speaking English or Spanish at home, but they only are exposed to that language entirely. Their friends speak the same language. Everybody they interact with speak the same language. Another group of children where their parents speak one language at home, their friends at school speak a different language, their nanny speaks a different language, and so on. What they noticed was they took, as a researcher, for example, they took some apples, they put 2 apples between the children and themselves, and they put a few apples behind them. And then they asked the children, how many apples do you see? And consistently, they were blown away by this response. For the children who spoke only one language and were exposed to one language, the children always gave account of the number of fruits that were in the room. But for the children who spoke the one language but got exposed to other languages, the children were thinking differently. They would say, obviously the person asking the question cannot see the fruits behind them, so they would only talk about the number of fruits between the person asking the question and themselves. The researchers are kind of intrigued by it, but they're thinking maybe these children are thinking a little bit beyond themselves, and they are thinking about the other person's point of view. I'm not a language expert, a natural language expert. I'm not an expert, period, but I love programming languages. But I can tell you one thing. When I started learning multiple languages, I started thinking very differently. And the reason for that is, to me, language design is the way we design our program, and knowing different languages helps us to define the languages, design with the languages very differently. So I will say that the amount of time we need to learn a new concept is inversely proportional to the number of diverse ideas we've been exposed to. So learning different paradigms exposes us to different ideas. Learning different paradigms exposes us to different line of thinking. So the more we think differently, the faster we learn to think differently. The less we are exposed to different things, the harder it is for us to change when the language we are using changes already. So this is one of the reasons I go out and learn different languages, is because I want to learn differently, but I want to learn quickly as well when I'm learning these different languages. So from that point of view, I would say, learn different language not to use them all, but to be able to adapt to the change quickly and easily as the languages we use evolve. So learning different language actually accelerates your time to learn the language you program in, and there's a lot of benefit to it. So diversify your knowledge portfolio. That's very helpful in the long run. So don't wait for the future. It's already here, and we can really do well by learning different languages and adapt very quickly. And I hope that was useful. Thank you so much.